Okay, here's page 2 of our differential equations. It was really called a review quiz, but who knows. Anyway, here we have the rate of change is given to us by this equation. So you're supposed to be able to recognize that this is a logistic form of our differential equation. Okay, this is in the form of Kp times L minus P. Okay, so this is our logistical form. So what are the values of the population that is increasing at a decreasing rate? So this means if it's increasing at a decreasing rate, our function is concave down. Okay, it's important to be able to understand what those words mean. So if we look at our graph of all of our logistic functions, right, we have some type of a carrying capacity, right? This is what they call L. In this case, that's 1,000. That's the L spot. We don't know what the initial value is, but we know that it increases up to a point and then it starts to decrease. Right? This is what all logistical growth happens. And this point here, this is the maximum growth rate, okay, also known as the inflection point, is always at half of L. So in other words, this one occurs at 500. Okay, so if we look at our graph, we are increasing at an increasing rate, right? This is concave up, increasing at an increasing rate, and then after we are increasing at a decreasing rate, right? Our graph is concave down. So the answer is going to be between 500 and 1,000 population. Right, that is when our graph is concave down, increasing, but at a decreasing rate. We are not growing as fast as we were before. Okay, so it's important to recognize this as a logistic equation because that makes all the difference in our problem. Okay, here we have the rate of change is modeled by a logistical differential equation. Okay, fantastic. The maximum number of people on the beach is 1,200. Now that's your carrying capacity, that's your L. And the number of the people on the beach is 200. So at the population at 0 is 200, and our population is decreasing at a rate of 400 people per hour. Which of the following best describes the differential equation? Well, looking at this form, right, this isn't even in one of our differential forms, so that's not even going to be right. Okay, nor is number 2. This is not a differential equation, that's just a linear equation. So the rest of these, well, they look pretty okay, okay, believe it or not. So let's do one thing. We know that dp equals 400 when p equals 200. So we're going to plug in our p-value into each of these equations and we see which one's going to work. Okay, so we had 200 people, that was the population. When there were 200 people, there was a 400 rate, right? That's the rate, dp dt. So let's see, does this over here equal 400? Right, that's the question. Does it equal 400? So 200 times 500 divided by, that's 2/5. And 1,200 minus 200 is 1,000. So 2 times 1,000 is 2,000. 2,000 divided by 5 is 400. Sure enough, this one's going to be the correct answer because when we plug in our two values, the left side equals the right side. Okay, so if that wasn't true, then we would try to plug in 400 here and 200 there, and then we would try to plug it in here and here, right? So you just keep trying to plug in your things until you see the one that actually works. Okay, that's a test-taking strategy. Let's look at page 3. So here's page 3, and it starts off with this multiple guess. The number of antibodies, Y, in a patient's bloodstream increases according to a logistic, imagine that, a logistic differential equation. That's what we're testing over. Which could be the differential equation? Okay, so which one is in the correct form? Well, this is not it. That's a linear equation. This one, dy dt, no, t is our time. No, it's not going to be that, right? Population are antibodies, so y should be the variable on the right side. Well, here's a y, but that's still a linear equation. This one doesn't have our kp times L minus P business, right? It's missing the y. So this one is the only one that's in the correct form. Kp times L minus P. So this is the maximum, that's the carrying capacity, and we would have a growth or a constant proportionality of 0.025. Okay, right? Antibodies are the y values. That's your population of things that, well, that increase. I'm not a doctor, so I don't quite know. But y is your population of things, so E. All right, what do we got here? Consider the differential equation, dy dx, and let this be a particular solution. F of -1 equals 2. Okay, so we have dy dx is the negative of xy squared divided by 2. Okay, so it wants a slope field. Okay, so we have 12 points. Let's start with the 0, 0. Right, when we use 0, 0, that's 0 times anyway, that's 0. Okay, in fact, anytime x or y is going to be 0, right, because we're multiplying on top here, anytime x or y is 0, we're going to have ourselves a 0 slope. 0 divided by 2 is 0. So at all the zeros, all these ones at 1, 0, at 2, 0, at -1, 0, all these points, as long as there's a 0 in your coordinate, we're going to have a slope of 0. So what about the other ones? What about -1, 1? Well, that means we have the negative of -1 times 1 squared divided by 2. Okay, so this is -1, of course. Negative of -1 is positive 1/2. So this one has a positive 1/2 slope. Okay, what about -2, 1? Right, so that's -2 times 1 squared divided by 2. So negative of it, this is 2. 2 divided by 2 is 1. This has a slope of positive 1. Okay, we're going to do that for all of these. So over here, when 1 is 1, this is going to be -1/2. This is going to be -1 as its slope. Okay, this one's going to be, what is this point right here? This is 2, 1. So the negative of 2 times 1 over 2, which is -1. Okay, so we're plugging in all of our coordinates into our differential equation, and we're seeing what happens. So at 2, 2, that's 2 times 4 over 2, -4. So this one's going to have a slope of -4. That's going to be pretty steep. Okay, so that's a slope field, right? We got to figure out what the slope is at all of those places. Write an equation of the tangent line at x equals -1. So we need the y value, we need the slope at -1, and those are the two things we need to write the equation of a tangent line. So when x is -1, we're told that y was 2, right? That's up here in the initial condition, f of -1 equals 2. And then the slope when x equals -1, right? That's our dy dx value here at the point -1, 2, right? So that was this one. The slope at -1, 2 was, no, it was not positive 1. The slope at -1, 2, did we do -1, 2? Where's -1, 2? That is, oh, I didn't do -1, 2. Shame on me. The negative of -1 times 2 squared divided by 2 is going to be 2. So this has a slope. This has a slope of 2. Okay, this one, that doesn't look like a slope of 2, does it? Up 2 over 1. That one needs to be a little steeper. That one's a 2. This one's a 1. Okay, so we get the slope at our value, and we get the y value. So, okay, y equals the slope times x minus negative 1, or x plus 1 plus 2. Right? That's our slope times x minus x0 plus y0. Right? That's our general equation for our line given a slope and a point. Okay, now comes our algebra. Find the solution to our differential equation. So we start with dy dx equals negative xy squared over 2. Okay, separation of variables. We're going to divide both sides by y squared. Okay, so that puts y squared in the denominator, and we're going to multiply both sides by dx. Okay, so we have dy over y squared equals negative x over 2 dx. Okay, separation of variables. The dx comes over here, and the y will go over there. So we're dividing both. Negative 1/2, negative stays over here on this side. Okay, now we do our calculus. We take the integral of both sides. In fact, because negative, I'm just going to, we'll write it here. Okay, so let me rewrite this as the integral of y to the minus 2. Okay, because I don't really like 1 over, so y to the minus 2 equals negative 1/2 of x. Okay, remember, divided by 2 is 1/2 times x. So this whole thing is a negative 1/2 x times the integral. That makes it a little bit easier, maybe, to do. Okay, so now let's take the antiderivative of y to the minus 2. So we add 1, negative 2 plus 1, and multiply by the reciprocal. And over here we have negative 1/2 of x squared times 1/2 plus c. Okay, so we add 1 to the power, so this is 1, 1 plus 1 is 2, and we multiply by its reciprocal. So this is negative 1 over y equals negative 1/4 of x squared plus c. And now we have the initial condition that f of negative 1 equals 2. So negative 1/2 equals negative 1/4 of negative 1 squared plus c. Well, negative 1 squared is just positive 1. So that doesn't change much right there. And now when I add 1/4, negative 1/2 plus 1/4 is negative 1/4. So we have a c value of 1/4. So we're going to come back into here and replace that c with negative 1/4. So negative 1 over y equals negative 1/4 x squared minus 1/4. Okay, solve this for y. So let's multiply all these things by negative 1. Right, multiply everything by negative 1, and that changes everything to a positive because they're all negative. So there we have all of them as positives. Now I'm going to multiply both sides by y to get y out of that denominator. 1 equals 1/4 of x squared plus 1/4 times y. Now I'm going to divide by this whole entire thing. So I end up with 1 over 1/4 of x squared plus 1/4 equals y. No, that's not a gorgeous looking thing, right? It's not gorgeous, but it is in fact correct. Okay, so you could do some algebraic manipulation on this if we wanted to. We might get 4 times 1 over x squared, or 4 over x squared. And then the reciprocal of 1/4 is 4. So that, you might see it written like this. 4 over x squared plus 4 equals y. Okay, well there's page 2. Wow, that went off a lot. Of your review. Excellent job. One more page left.